okay, well, I want to talk about the history of the universe, and I see an awful lot of people have come out to find out what that is. So there's an awful lot to say, so I'm not going to be able to say the whole thing. But here on the picture, what we have is the telescope that I'm going to talk about, and you see something that might be surprising. We see something that looks more like a solar energy concentrator. It's a gigantic hexagonal mirror made out of 18 smaller hexagons. And if we can use metric units today, is that all right? 6.5 meters across, and then a non-metric unit, the telescope is protected by a giant umbrella of 5 layers, and it's as big as a tennis court. So this is a joint project of NASA with the European Space Agency and Canadian Space Agency. So a lot of people in a lot of countries are contributing to it. So we are building it on behalf of everybody that lives here. At least 10,000 people will be using it as observers. And many thousands of engineers and technicians and scientists have already been busy building it. So, however, I want to start even before that with how did I get to be a scientist? So I grew up on a research farm of Rutgers University in northern New Jersey. So this is how I got interested in the sky. That thing that looks like a barn did actually have bulls in it, but it also had research labs, chemistry, all kinds of things that my dad was working on. He was a geneticist. So my parents took me to the Museum of Natural History in New York, and I saw the planetarium show, I saw the giant meteorite, I saw the dinosaur bones. I got to do something about this. So I got excited about science very young. So now I've got a chart summarizing what we don't know. So I think most people believe these days that quantum mechanics really is the fundamental thing that describes our universe, that particles have wave nature and waves have particle nature. And we've got the equations. We've been perfecting them for almost a century now. So on the other hand, they're pretty darn hard to solve. If somebody says, here are the equations for your universe, you cannot just say, then I know what's going to happen. So we pretty soon get into basic science, applied science, and finally engineering. If you want to say, what is concrete? You have to go measure. If I read another book, it might be called I Have to Go Measure. So we know the universe was very compressed and very hot when it was young. This is what people call the Big Bang Theory. I'll come back to that because it's a really rotten name for the story. We know there is instability everywhere. In school, you would learn in physics that things do not spontaneously heat up. But of course, the universe spontaneously heated up. The first one was gravitational forces pulled things together and made compact objects. Gravitational energy can be released by friction. So when an Earth satellite orbits around the Earth, it loses energy and heats up at the same time. So who'd have thought that? Well, in astronomy, we say gravity produces a negative specific heat, which means unstable. So the universe is unstable in a lot of ways. The universe is very large, very probably infinite in extent, although who could know? You can't see infinitely far. But at least the equations are simpler if it's infinite than if it's finite. So let's call it infinite. Very old. So even things that are very unlikely seem implausible to us, like spontaneous formation of life, may have happened here. There are many places where it could have happened, and we might not be the only ones. Big question. So there is an interesting question about information. We now have the mathematical theory of information, and since the 1940s. But we've now been discovering where information is stored. When I was a little kid living on that farm, my dad told me that living things are made of cells and we have chromosomes, and that's where the information is stored. Nobody knew how that worked. In the early 50s, we didn't even know there was a double helix. Now we can read the code letter by letter, but we don't know what it means to our cells. That's a very long project to find out how that works. So I put in here also evolution, because it's the ability to copy the information from generation to generation while making mistakes that allows for evolution. And I mentioned survival of the lucky, because when Darwin told us about evolution, he called it selective, what was his word? Natural selection. People immediately said, well, obviously human beings are the best. We are the pinnacle of history. Was all aimed for us to be here, to be the top of everything. They didn't know what the geneticists are now telling us, which is our ancestral population was down to a few hundred people somewhere in southern Africa, so that if they'd been a little bit less lucky, we wouldn't be here at all. So think of yourselves as lucky as well as perhaps fit. So anyway, a lot of things to think about there. Another interesting puzzle is what I'm calling the nested feedback loops. Each of our cells is operating as a feedback system. So, have I got enough food? Have I got the right shape? So the cells have a vast number of little sensors in them and feedback systems. It works so well that you can hardly tell that I'm a different person. So my teeth are the same atoms that I had when I was little. The chromosomes in my nerves, in my brain, are probably the same, but almost all the other atoms have been exchanged for new ones. But you still think I'm the same guy, maybe. So that's a pretty big mystery, and if we can understand that, maybe we'll understand a lot of other things. Anyway, the balance of nature that we now have from these feedback loops is, however, temporary, because most feedback loops are not guaranteed to be stable. So if you're an engineer, you know a lot about that. So now that's all of what we don't know. So how do we get at what we might want to know? Well, how about telescopes? I've got here a drawing from Leonardo da Vinci from about 1513, and some people believe this proves that he knew about telescopes, almost a century before Galileo had one. So I can't prove that. I can't read his writing. I don't know what he meant, but there are people who have studied this carefully and said, yeah, that's what he meant. If you built a reflecting telescope with this story, you would be able to get magnification and so forth. And we know he did work on lens grinding machines. He was very interested in optics, so maybe. But it wasn't until 1609 that Galileo had a telescope, which, by the way, he also did not invent, but he perfected it significantly, and he was able to completely change the history of science by showing that Aristotle was wrong. Of course, he got to have an argument with his friend the Pope and got to stay home a long time. But he was right, of course. He didn't say, I made a mistake. He did make mistakes, but not that one. Among other things, he tried to measure the speed of light by having people with lanterns and shutters stand on mountaintops, but it was way too fast for him and they couldn't find it. Nowadays, we know what it is because we've defined it. We've measured it for a long time, and now we've defined what it is. But at any rate, now you can use light to look back in time. So each of us has a time machine right in the front of our head. We look at things as they were when light was sent out to us and not as they are now. So if you look at things that are really far away, you can see way back in time. So if you could look at the center of our own galaxy about 25,000 years back in time, if you could look all the way back to what we call the Big Bang, almost 15 billion years. So how would you know how far you're looking in time? Well, you have to measure space. So you do your trigonometry, as the ancient Greeks knew how to do, and they were able to do it well enough to measure the distance to the moon, and they got it about right. They would have understood quite well the standard candle method that astronomers have to use when the triangles no longer work. So if you know and can argue that that candle is identical in brightness to that one, but this one looks fainter, you say it's farther away, and now you can measure ratios of distance this way. So after centuries of effort, we can now do this pretty well. And now we want to know about motions. So things do move, but a lot of things don't move fast enough for you to notice. So if you spread out the sunshine with a prism and do it very carefully, you'll get a rainbow with dark bars across it, and these dark bars are due to the chemical species in the surface of the sun. And if you look at another star and you say, I get the same rainbow, only fainter, well, it's because it's further away. If it's similar enough, you say, well, it's a star just like the sun. Same chemistry, same temperature, same pressure, same everything. But quite often what we'll see is that all the wavelengths are shifted over to either shorter or longer than they should have been, and that we say it's because the thing is moving toward us or moving away from us. So we now measure speeds of motion. 1929, we got the first, oops, I'm going to skip over this one. In 1929, Mr. Hubble was making a graph by measuring the speeds of motion and estimating the distances of galaxies. So here he is staring through the eyepiece to keep a guide star on the crosshairs to make sure he'd get a sharp picture. So he drew us this graph in 1929. Each of those dots represents a galaxy being 100 billion stars, more or less, orbiting a common center. Distance measured on that direction, speed of motion away from us in the vertical direction. Had not yet been properly trained in what units to use. But at any rate, you do see a trend here. The farther away they are, the faster they're going away from us. And this was a big shock to an awful lot of people. So I skipped over the story of this, but Einstein had written his equations of general relativity, and he'd applied them to cosmology, and he said, basically, he knew that the universe must surely be static. So he introduced an anti-gravity term, which we call his lambda constant, to balance the attractive force of gravity. And so he knew the universe was static. George Lemaitre and Alexander Friedman had both solved Einstein's equations differently, and they said the universe must surely be expanding and cannot be static. So they were pretty pleased to see, well, Lemaitre was pleased that Friedman had already died. But at any rate, he didn't get to find out he was right. But the universe must be doing this. The distant galaxies must be running away from us with a speed proportional to distance. So how old is the universe? You can get that from this graph. Divide by this distance by the speed, and you get, in Hubble's chart, about 2 billion years. So the first time we knew the universe had an age at all. Now, the age was wrong, because he used that standard candle method to get the age, and the nearby candle was a different kind from the faraway kind. So it took us a long time to find that out, and we were still arguing about it until pretty recently, when we used the great Hubble telescope that we named after him, and we now are still arguing about it, only the error bars are small. So anyway, the expanding universe we can trace back to 1929 observations, and he didn't do the whole thing, but he did many, many important parts. So this is what we call Hubble's Law. Hubble didn't call it that. Anyway, so if the story is correct, then what was the universe like when it was young? Well, you could imagine that it was cold, or you could imagine that it was hot. If you take the movie of the expanding universe today and you run it backwards, you say, well, everything will crush everything else. It probably was hot when it was young. And that then leads to the prediction that we should be able to see a few things. We should be able to calculate nuclear physics. We should be able to get the ratio of hydrogen to helium from those ideas, and we should also be able to estimate a temperature of the heat that would have been there then and should still be here today. So there should be heat radiation, electromagnetic radiation filling all space, if this is true. So in 1965, it was discovered by accident. Penzias and Wilson got their Nobel Prize for finding it. In 1970, I was looking for a thesis project to go, and the idea was, oh, let's go measure that. A graduate student should be able to make some progress. My thesis project didn't actually work right. I got a job at NASA, and I'm going to be a radio astronomer. However, that summer, NASA asked for proposals. This is like 5 years after the Apollo landing. What are we going to do for fun after that? So they got 150 proposals or so, including one from our team, and it eventually went into space, and this is what it looks like. So our job was to measure that cosmic heat, see if it's the same color as predicted by the expanding universe story, and does it have the hot and cold spots that are necessary for us to exist. So there it is. It's still up in space, although it doesn't really probably look like that anymore. So our first scientific result was this one. This was, Paul's alluded to this one. This is a measurement of the spectrum of the cosmic microwave radiation. So here's the wavelength of 1 millimeter, the brightness on the vertical direction, the frequency in cycles per centimeter on the horizontal direction, the prediction of the expanding universe story, the smooth curve. It's called a black body curve. And eventually, although we got a standing ovation for the 1% error bars we showed here, the eventual error bars came down to 50 parts per million. So the best test that's been done yet of something like that. So why was it so important? It basically meant that the expanding universe story is probably right, and that it was hot when it was young, which we weren't 100% sure of. Second big discovery was this one. 2 years later, the picture to focus on is this one. This is a map of the entire sky compressed onto an oval, and the hot and cold spots are very, very faint. Total temperature we measured is about 2.7 Kelvin, 2.7 above absolute zero. Take out the local effects and you are left with hot and cold spots measured in microkelvin. And so the typical spot's about 30 microkelvin hotter or colder than the average. So Stephen Hawking saw that chart. He said that's the most important scientific discovery of the century, if not of all time. So now we can tell you a little better why he would think that. Number one, as Paul mentioned in the introduction, if we didn't have spots like that, we would not be able to explain how come we exist. So the idea is that those spots represent density variations of the primordial material, that the dense regions have enough gravity to stop the expansion of matter and pull it back in and compress it into future galaxies, stars, planets, and people. So we're here because of those spots. We now also can appreciate that most of them come from cosmic dark matter, which only astronomers have so far detected, but there are experiments going on in many places trying to turn up some of it in a laboratory. Third thing is, if we knew what made the spots to begin with, we'd be having a good clue about quantum gravity, but we're not there yet. So anyway, if this is true, we should be able to calculate what happens next. We should be able to simulate in a supercomputer how gravity acting on that primordial material will stop the expansion and pull it back in and make it galaxies and so forth. So I have now a supercomputer simulation to show you. If we have control of the lights, it'll be better if we can turn them down. I forgot to ask for that. But at any rate, we'll show the movie, and you will see galaxies growing before your very eyes. Is there a switch over here we can run? Yes, thank you. This will be a better one. We will see in the simulation a box of universe. What the computer folks have rotate in front of our eyes so we can see the three-dimensional structure. And they've removed the fact that it's really expanding, but you can see the structure growing. Oops. Here it is. The movie shows that even in the the first half billion years, galaxies are growing from that primordial spot pattern. So this simulation is already a few years old and probably not completely accurate, but it's very beautiful. And it tells us some things that we didn't fully appreciate in advance. The gravity operating on random spots can produce these amazing stringy structures. The galaxy is arranged on threads through the sky and sheets of material. See, once in a while you see it edge on sheets of material. So a galaxy like the Milky Way would be one of these little specks orbiting around there. And the galaxies end up in groups and clusters. There it is, like a flat sheet in space. Gravity did that. I don't think very many of us astronomers would have imagined that could happen just because of gravity. You see here several billion years in, there are lots of explosions for several reasons. One is that old stars that are big enough will blow up. One is that black holes form in the middles of galaxies, and we don't know how. But when stuff falls in, enormous amounts of gravitational energy can be released, and it comes back out. So these explosions would be sterilizing to any life that were in the neighborhood. But we weren't there yet. The solar system was born when the universe was about 9 billion years old. And the explosions had sort of petered out a lot, partly because the density of the universe is diminishing with time. So in this part in the movie, this is roughly when the solar system turns up in our own particular galaxy. The movie also shows you things we couldn't possibly observe in nature because we can't wait billions of years to watch something happen. So it has the virtue of that. But it has the unvirtue that you can't tell if it's true too well, except by taking pictures of the sky to see, is it really like that? So people are very busy trying to take the predictions of synthetic models like this and say, well, if you build a telescope, what will you see? So now we can say, yeah, the Big Bang story that we call the Big Bang story is probably about right. But I wanted to emphasize that the Big Bang is not a good name. Because if you hear the story about the Big Bang, it makes you think of a firecracker that happens at a place and a time. And what astronomers have in mind is the exact opposite. Oh, thanks. We have in mind that the universe is infinite, not happening at a place. Universe never was a point. We can describe a singularity, but that doesn't mean you can get to the point. You can only get close. So you can't get to a place called infinity. You cannot get to zero time. So there's no first moment, no creation event that we can actually measure. So anyway, many people get credit for this. It's an enormously difficult computing job, but now we can do it. So how do you know if it's true? You build telescopes. Here's one. The Hubble telescope is up there. It's working beautifully. It's 27 years old. People have been up to visit it 5 times. As you know, it was not in focus when it was launched. We had to fix that. We made many improvements since then. When they first built it, we didn't have good CCD detectors or anything. We were expecting to put up intensified Vidicon vacuum tubes. You remember vacuum tubes? We used to have them. Anyway, Hubble is in great shape, probably run 5 or 10 more years at least. So here's one of the pictures they took with it. It is called the Hubble Deep Field, or now Ultra Deep Field. They chose a particular spot to look at where there was almost nothing to see. There's one star that you can recognize here, the one with the blue and red spikes sticking out. The rest of these dots are galaxies. So they're many colors. The redder they are, the farther away they are usually, because of the expanded universe stretches out the light from the distant galaxies. And it was a huge surprise to astronomers that this is how it is. Number one, there were more galaxies than we thought would be there, and number two, they started growing right away, as the movie showed us, but we didn't know that 27 years ago. Pretty soon after we got this picture, astronomers said, we would like another telescope, please, that's more powerful, that we would be able to use to see the first galaxies growing. So why can't you see them on here? Well, number one, the Hubble isn't big enough to see the little faint dots that are far away. Number two, it doesn't see long enough infrared wavelengths to be able to see the reddest galaxies, the ones that are expanding away from us so fast that their light no longer has any visible wavelengths at all, but all infrared. So please build us another telescope. And the guys that wrote, the people that wrote this report, they hit it off very well with NASA. And so we are now building that telescope that they asked for. So a few other surprises to talk about. In '98, we discovered that there is something called dark energy. That we always believed, or most astronomers believed, surely the expansion of the universe is slowing down because gravity is pulling the galaxies together. And it did that, actually, according to our story, for the first 9 billion years of the universe's expansion. And then it started to speed up, which we ascribed to something we call dark energy, which actually is completely meaningless. We have no idea what that is, but we have measured its effect. So anyway, these are the people who went to Stockholm to get their Nobel Prize in 2011 for this discovery. Now, we astronomers are very busy pushing this harder. We have 2 satellites that are being prepared that are going to measure it better, and the Webb telescope will also be used to measure it better. So anyway, big mystery, not likely to be solved soon. We can measure, but we won't know what it is after that. So here's a picture of a nearby galaxy that's taken with Hubble. And I love this picture because it shows lots of things about our history. If the solar system were here, it would be way on the outside edge. You see the blue areas are where brand new stars have been born, blue young hot ones. The pink areas are where stars are being born, and the brown areas are where there's a lot of dust in space that's stopping the starlight from getting to us. It's also something that will happen here. This little galaxy is about to collide with that one, and they were going to combine into one. What I love about this one is here a picture taken in 1845 by Lord Rosse, who was an Irish astronomer. And he had a giant telescope. It was called the Leviathan, and the mirror was this big, a 6 feet across mirror made out of metal. And so that was the biggest for a long time. And he was able to draw this, make this, and it does resemble very well what the Hubble telescope showed us. Here's a picture of a star that blew up on July the 4th, AD 1054, which we know because astronomers around the world could see it, and the Chinese records still survive, so we know what day it was. You could see it in the daytime, it was so darn bright. And then it went away. They called it a guest star. They knew it was different. Anyway, it's important to us because this is an example of how chemical elements, aside from hydrogen and helium, made it here. When you look in the mirror in the morning, you are looking at stuff that went through some process like that. So every morning you say, those atoms, you've been traveling for hundreds of millions of years in space, hundreds of millions of light years perhaps, before you came to become me. Think about that. So how do we know what happened then? Well, we build more telescopes. This is a telescope called the Atacama Large Millimeter Array, and it's a collection of radio telescopes in the desert in South America. And they built it so they could take this picture in the upper left. This is a picture of a new star has been born, and it's being surrounded by rings of dust grains orbiting around. And our story here is that we think there are planets growing in these dark areas in between. So this is an example of how a solar system with roughly 9 planets might be happening. And if you were to wait for a fraction of a million years, the dust would mostly go away and the planets would be left, and eventually you would have something sort of like our solar system. So we're beginning to understand how the solar system might be formed. This is one way to go at it. This is a possible history of the solar system. When Newton gave us the laws of motion, people immediately said, well, the solar system runs like clockwork. And so, however, I mentioned earlier that gravitational forces can make things unstable. So this picture shows you the orbits of the 4 giant planets, Jupiter, Saturn, Uranus, and Neptune, along with a vast number of comets and asteroids that are debris left over from the formation of the early solar system. And this is all simulated. But look at that. In this version, it is unstable. The little rocks go flying every which way, and a lot of them hit us. So this is among the catastrophes that was mentioned in the abstract. We probably wouldn't be here without that. So among other things, that's probably how we got the carbon, which is volatile, and the water that we need to have life and an ocean. So catastrophe necessary for our existence. So we know the Earth was bombarded for hundreds of millions of years by rocks, and then it mostly stopped. So this story would explain that. So what else could we do? Well, let's build some more radio telescopes. People don't know yet what this is going to show, but we are now building 2 pieces of a telescope called the Square Kilometre Array. Can you imagine how you would do that? Well, they decided to build it out of separate dishes and separate dipole antennas and connect them together with computers and cables. And so both of them are being built, one in Western Australia and one here in Western South Africa, both places where you can't get any cell phone service, and that's good for astronomers. But a thing to mention about this one is it is going to be so powerful that you could imagine if there were a civilization on a nearby planet around another star, we'd be able to pick up their airport radars. I don't think we're going to see them, but we got to look. So just a hint as to what's coming. So now I want to talk about the Webb telescope. Here it is, another picture of it. There's the giant golden hexagon, 6.5 meters across. The telescope is being built by a team led by us at NASA Goddard, along with our main contractor, Northrop Grumman, and our international partners. We have 4 instruments on board that are coming from different places around the world. Europe, Canada, and the United States. Operations will be in Baltimore at the Space Telescope Science Institute, just like we do the Hubble Space Telescope. The telescope is going to be cold, around 40 Kelvin. And why do you make it cold? So it doesn't emit its own infrared. You're transmitting 500 watts of infrared power, and if we were to make a telescope at room temperature, it would glow like crazy. So we don't want to do that. So it's going to be cold. It's going to be launched by a European rocket called the Ariane 5. It's a good one. They've had 75 good ones in a row, and that's about as good as we get in our business. So now we'll go on and talk more about the telescope. How do we get it? Well, first we put it together in our clean room at Goddard Space Flight Center. So there it is, the telescope part with the instrument package on the back. Here we have the telescope in a giant plastic tent where we're carting it over to the shaker. So we have to do something you don't have to do. We have to make sure our equipment will survive several G's of launch vibration and a whole heck of a lot of noise, like 150 decibels of noise. So we have to put it through a test, hope it don't break it, make sure that it will survive the launch. After you're done with that, you put it in the big mailbox, take its truck around the highway to the Air Force Base near Washington, fly it on the C-5C aircraft down to Texas, undo it, put it in the giant vacuum tank in Texas. This is a vacuum tank which we built for the Apollo program. So the astronauts could practice walking down the ladder onto the surface of the moon. We had to augment it with cryogenic cooling. Right, we did that, and the telescope is almost done with its tests. It survived Hurricane Harvey. And we're going to put it back on the airplane and fly it to California this fall, where it will meet up with the rest of the observatory, which is being prepared at Northrop Grumman in LA area. We will verify that it unfolds properly in California, button it up, put it in a different mailbox, and put it on a ship, which will go through the Panama Canal on its way to the launch site in French Guiana in South America. And of course, they put it there because it's near the equator, and it's European territory in South America. So we'll push the button in about a year and a half in spring 2019. Up it will go, and we will unfold it again in outer space. This is our job, to make sure this will happen. Where are we going to send it? We're putting it out at a place called the Sun-Earth Lagrange Point 2. So this is definitely not to scale. There's the Sun, there's the Earth, 150 million kilometers apart. Here's the Lagrange Point 2 is 1.5 million kilometers away from us. It has the advantage for us that if you put up your umbrella, the Sun, the Earth, and the Moon are all in the same direction, and so you can hide behind it, and the telescope will always be cold. So this particular point, all 5 of these points, are places where the combined gravitational force of the Sun and the Earth will pull the object around the Sun once a year. So it stays overhead at midnight for the duration of the mission. So this is our scary movie. We launch it all folded up, then we unfold the solar panels, because that's what we use for electric power. We'll have to do that right away. We unfold a little antenna dish to talk back to our big ground station in the desert. We begin to unfold the carbon fiber structure that holds up the sun shield, the umbrella. It's all done by remote control. No astronaut is anywhere nearby. And this is done while we are on the trip. So within a few hours of the launch, we begin to do this. It's extremely complicated. And if it weren't possible, and if you could do the science in some other way, we would. But I guess you're accustomed to extremely complicated things. Our challenge is that we don't get to go fix it. So the last step is pulling on cables with motors to separate the 5 layers of metallized plastic that form the big umbrella, the sun shield. So then when they're all deployed like that, the telescope will begin to cool down. So we selected a company called Northrop Grumman to do this work. They said, well, this is definitely not the most complicated thing they've put up in space. One thing about the picture is inaccurate. The telescope would be actually in the dark. You would not be able to see it. So it takes a while after this is achieved for the telescope to be cooled down and focused. It takes altogether 6 months to get the whole thing set up to start taking scientific data. Okay, computer. So what are we going to point it at? We have not chosen all of the targets. We have chosen some of them. This is an example of the place that NASA has already looked with the Hubble. It's called the Eagle Nebula. It's a place where stars have just been born inside these dusty clouds of gas. And astronomers would say, well, what's going on inside? Can I please see inside? And the answer is yes. If you want to see inside, you have to use longer wavelengths, because the longer wavelengths of light will actually go around the dust grains instead of bouncing off. And so that's what we get when we do infrared. Hubble has some infrared capability, and you can already see it's a dramatically different picture. And you can begin to see through the dust, but it's still there in your way. So dust is both an obstacle and a cause for the formation of stars. So somewhere in there, probably stars like the sun are being born, and it would be good to find out how that works. We will be looking at Jupiter, but Jupiter will look more like that to us than that. I put this here just to remind us that if you can go there with a robot probe, it's much better. This is a beautiful picture of the North Pole of Jupiter, which you might never have seen before, but it's amazing and gorgeous and beautiful in every way. These are little blue clouds, are storms, and nobody had ever seen it until we sent the probe. So it's good to get there and up close and personal. we will certainly be looking at Europa. This is a picture taken by the Galileo mission, which went to Jupiter and orbited around and took pictures of the various satellites. This one is known to have an ocean covered with ice, and there are geysers, warm water geysers, that are coming out in places between these cracks. So now we say, well, wouldn't it be good to go land there and see if the ocean is alive? How would you know? Well, maybe the first thing you try is go fly through the water that's coming out and take a sample of the gaseous water that's coming by. Eventually, maybe you should go land nearby where it's coming out and stick in a probe and find out what's in the water. That's much, much harder, but we're already working on plans to do the first part, to orbit around and try to fly through the water spouts. This is another example of a thing that you cannot do very well from a distance. This is I put this here because when people said we're going to send a probe to Pluto, I thought, well, that's probably not very interesting. It's going to be a round rock. Now we know it's not a round rock. It's covered with ice. These are water ice mountains, and this is nitrogen snow lying on the ground. And it is so amazing and interesting, and just shows the complete lack of imagination of astronomers. And most of us never guessed it would be anything like this. So, and also how completely remarkable nature really is. So we will be looking for Pluto's cousins out there. He has been voted off the island of big planets, but he has thousands of cousins out there, some of which are already known to have atmospheres and their own little satellites. So we will be studying those guys. If you already know that it exists, we'll be able to learn a great deal about it and get a spectrum of each one. We'll be looking for these kinds of events. If you know when this is going to happen because somebody else has told you to look at a particular star, when a planet is going to go in front of the star, then you can use this to learn a lot about the planet. So what can you learn? Well, some of the starlight goes through the atmosphere of the planet, if it has one, on its way to the telescope. So you can analyze the chemical composition of the atmosphere of a planet around another star. So we already have a few candidates that are interesting. This is one, this one is called the TRAPPIST-1 system. The first planets on this one were found from the ground because the star blinked several times, and they said, we can see this happening, and they go around in just a few days. And they do that because the star is actually very small. It's about the size of Jupiter. Then we pointed our space telescopes at it, and we were able to say, yes, there are really 7 planets here. And this is roughly how big they are. And they go around 1.5 days up to about 20 days to go around. And the ones in the middle are roughly the right temperature to be like Earth, and roughly the right size. The colors that the artist has put here are completely imaginary. And we may, I don't know if we're going to get the colors, but we'll certainly try. So could any of these be like Earth? This is a good candidate to find out if any of them have water. We have the sensitivity to find out if an object like this does have water in its atmosphere, and maybe enough to have an ocean. So I don't know whether we expect an ocean out there, but we will certainly be looking. The ultimate goal, of course, would be to say, is there life on a planet out there? And you would be looking for signs like oxygen. And we don't think we can do that with this equipment. So Fermi asked in 1950, where is everybody? If space travel between the stars is possible, how come we haven't got any space aliens here? Although some people would say we do. Nevertheless, I don't think so. So how would we know? How come they're not here? I think the middle bullet basically says it's too dang far. So that probably means there's no warp drive, none of those things you saw on TV. And so it would take many, many, many lifetimes to travel as a human being, or even as a robot. So on the other hand, communication between planets far apart is possible. If you knew how to tune up your receiver, we could definitely have a conversation with a civilization nearby. We don't know, so that's how come we're working on the search for extraterrestrial intelligence, and it's awfully hard to do, so don't hold your breath. I don't think we're going to find it soon, but maybe if we pick up those airport radar signals, maybe we'll say we should try harder. So another challenge for us is we have been living with other intelligent life here for a long time, and we don't know what they're thinking. and what they're saying to us. If your dog knows what you think, but you don't know what he or she thinks, then we're actually not that far along in this project. So how likely is it that there are other civilizations out there? Well, at least here in the solar system, we know that the Earth is a very special planet. It's the only one at the right temperature. It's the only one with a nearly circular, well, they all have nearly circular orbits, but it's the only one with the right temperature. It's the only one with a very large moon compared to the planet. So that seems important for the geometry of our system and stabilizing our spin axis. It may be responsible for the fact that we have a big magnetic field which protects us from solar and galactic cosmic rays. We've got just enough water to cover up most of the ocean floor and still leave some continents sticking up for us to live on. We have just the right amount of carbon and nitrogen to make stuff. Our star is just the right temperature to cause photosynthesis to occur in the materials that we know about. Is that all necessary? Who knows? But it's at least unusual in the solar system. We are also the only ones that have plate tectonics. So the geology is continually shifting under our feet, and it's possible that this is the reason why we have life. As the undersea hydrothermal vents are tagged as one very likely location for the first life forms to occur here. So who knows? We'll be working on that for a while. So what else are you going to do? We're going to build more big telescopes. So I can imagine putting up a big telescope in space, but it's possible to imagine putting up a much bigger one on the ground. We are already embarked on 3 truly gigantic telescopes on the ground, one 24 meters across, one 30 meters across, and here's the European one, almost 40 meters across. They've all been started, and so when those are going, I think you can expect enormous surprises. They are all based on using adaptive optics to compensate for the shimmering atmosphere of the Earth, and so when these get going in the next 5 or 10 years or so, we will have amazing discoveries too. So what comes after that? Well, NASA every 10 years sponsors a National Academy of Sciences report, along with the NSF and DOE. And we argue and argue and argue. We write a report saying, well, we think this is the next big telescope we ought to build, or the next big thing. So this is one of the candidates out of 4 big ones that we're already studying. This one is roughly twice as big as the Webb telescope and much more accurate. So if you could do this, you would be able to see an Earth-like planet orbiting as a little dot around a sun-like star. And then you'd be able to ask the question, are there chemical signs of life in the atmosphere of that planet? So could be done. This is really hard. It's probably as hard or harder than the Webb telescope. And so we may not get to do that one right away, but we will certainly have a big discussion. No. Here I just wanted to put up a chart about my friends. Ray Weiss in the upper left corner. Has he come to visit you already? Not yet. You'll be delighted when you can get him to come. He's going to be a busy man because he's now one of the 3 recipients of the Nobel Prize this year. He was also the chairman of the science team for the Cosmic Background Explorer satellite that I showed you before. So 1 man, 2 Nobel Prizes. Pretty amazing guy. He's the sort of guy who, when you see him, at least in the old days when you could take your stuff on the airplane, he would travel with his jacket pockets full of voltmeters, wrenches, screwdrivers, and things like that, because he was the kind of guy who would fix everything. And he has that sort of genius about physical things. So Kip Thorne in the middle predicted what we should, Barry Barish in the middle managed a lot of things, and Kip Thorne on the right predicted what we should see, and he was right about a lot of things, including they got about the right number of neutron star pairs. So recently, we just saw a neutron star pair occur and doing its merging, and there's the sketch many of you have seen before about 2 neutron stars merging together. It was unknown whether this would really happen. It took an amazing amount of optical science and high-powered lasers to make this work, but it does work. So we are now embarked on what we now call multi-messenger astronomy. This particular neutron star merger has been observed at gamma rays, X-rays, visible light, infrared, and radio waves. And as I understand it, there's something like 4,500 authors on the accompanying paper set that describes this event. So we've got a new territory of astronomy opening up. with that kind of thing. And here is another part of the new kind of astronomy we have. We are also embarked in this project. I'm not sure if people here are involved in it, but almost everybody will be eventually. This telescope is 8 meters across and has a 3.2 gigapixel camera. Every 3 nights they're going to map the whole sky that they can see, and they tell us they're getting 10 million things every night that have changed since last they looked. So we're going to need a lot of graduate students to find out what are those 10 million things. So we need to sort them out and say, well, this is interesting because, and then every now and then somebody will call us up at the Webb Telescope team and say, can we please point the telescope right over there because something very exciting has happened that we don't know anything about from before. So that's probably a good place to stop, although we could keep on talking. So maybe we'll stop and have some questions. Thanks very much for your attention. Okay, so we're going to turn up the lights. Thank you. Okay, so what's our plan for questions? Just wave your arms? That's the plan? Okay, wave your arms.
At the L2 point, how much of the sun is blocked by the Earth?
Oh, we're actually not going to the L2 point because the sun is, it's right at the end of the umbra. So a lot of the sun is blocked. I don't remember the exact amount, but it's right near the end of the full shadow. So we will orbit around that spot. We don't want to go to the L2 point.
Okay, all right. That was, I mean, obviously your solar panels are much less efficient with the cooling.
Yes, we don't need the extra cooling. We just need solar power. Yeah. We absolutely have to have solar power. We will guarantee that we do not fly through the shadow. Oh. Well, clearly the U.S. space program is bigger and more powerful than all the others combined. We have a big budget and we have a lot of success. But the others are gaining. The Europeans have a very different organization process, and the European Space Agency is much less chaotic than we are. But they also produce results. And they do things a little more systematically, and once in a while, a very great surprise. The Chinese have started a space program which is growing rapidly. And basically, as far as I can tell, they can do anything they want. They have to start a little farther back. They're going to be at least 50 years behind us getting to the moon. But they can do that if they feel like it. And I think they do feel like it. They have started in on radio astronomy and lots of other astronomy. They have just about completed a 500-meter aperture radio telescope. Similar to our Arecibo telescope, only bigger and different. So pretty much they can do whatever they like in China. In India, the Indian Space Research Organization has launched a probe to Mars, and they succeeded. In fact, they're the only nation to ever have a 100% success rate to Mars. All the rest of us had some failures, and the Soviets had all failures. So that's really good accomplishment for them. Japan has an active space program. They have launch vehicle programs that they make available. You can buy a Japanese rocket if you want to launch your payload. We've worked with them in partnership for NASA programs quite a long time. So there's an awful lot happening.
Yeah, thanks for the talk. So the Webb telescope is a fantastic piece of engineering. I wonder if you could tell us a little about the biggest engineering challenges you had to overcome, and what is the part of the unfolding process that people are most concerned about?
Funny you should mention that. The hardest part to begin with was always the mirrors, because we need, the telescope mass is about half what it is for Hubble. We have 6,600 kilograms to throw all the way out 1.5 million kilometers. That's the maximum the rocket can do for us. So getting everything light enough to go is a huge challenge. When we said we're going to make those mirrors that are almost as precise, but not quite as the Hubble mirrors, but 7 times the collecting area for half the mass, people laughed at us. But what we did, by the way, to get that is we issued competitive procurements. We said, okay, companies, you think you can do this? Prove it to us. So it took us 12 contracts to get one that worked. But we got one. And so that's why the mirrors are made of beryllium. I didn't tell you much about the mirrors, but the mirrors are beryllium. And the surfaces are about 2 millimeters thick. And there's a triangular web of reinforcements on the back. And there's a company called Tinsley Labs that knows how to make that happen and get the surface that we require. So they won't tell us how they do it. That's their secret. So what concerns us now? Clearly the unfolding of the big plastic sun shield is the hard part because it's so unfamiliar. We can't say it's just a hinge. It's a lot of hinges and it's a lot of mechanisms. The plastic has to be held down in well over 100 places to protect it during the launch. And then you have to retract all those things to let it go when you want to let it go. So that's a long process. So how do you make sure that's okay? You have 2 of everything, or you possibly can. Every actuator has 2 ways to actuate from 2 separate electrical systems. So we don't want to have to go there, but we have it. So it's clearly that's the thing that everybody worries about. More questions?
Yeah, you made a very interesting comment about dark energy, and what I understood is you maybe were a little bit skeptical about, that it was going to take a long time before we understood the energy of dark energy. So I was wondering if you could say a little bit about what you think are the most promising, probes in space for probing the nature of dark energy.
Well, what we can do is measure how much of it there is as a function of time. By measuring the acceleration of the universe. And then we deduce from that acceleration story what the dark energy must have been doing. So far, it fits Einstein's lambda constant perfectly. But we imagine if we can measure better, then it won't. And that would be telling us something very important about the nature of the source of it. Now, right now, I don't think we have very many ideas that come out with the right answer from theory. A few people do. And they say they get it right, but people don't usually believe them yet. So that's a theory question. Are we going to measure anything in astronomy that tells us what it is? I don't think so, unless, well, it's just too hard. We measured it already, and we've known about it for a long time, and, well, we're just not getting it. And so need better theory. So have you got any more Stephen Hawkings coming along? People are working it quite hard, but we just don't agree on it yet. There are lots more questions. You just aren't asking them yet.
I assume that you'll repeat the deep field up.
Oh, yes, we're definitely going to repeat that observation. It has been so exciting and so powerful and so surprising over the years. And the value of doing it again is enormous because you already know so much about those things. And you see something new and different, you say, that's really interesting. We'll do that again.
Same place?
Yeah, same place.
So how far back in time?
Oh, how far back in time? It depends on what nature gave us to look at. So we have the ability to see galaxies or supernovae within about 100 million years of the beginning of the expansion. So most of the way back in time. How far is that? Well, that's about 13.7 billion light years out of 13.8. So that's what we also call it in terms of redshift, 10 or 20 or 30. Depends on what nature gave us to see. There's a question in the back.
So last week we built Paul Steiner will the new telescope be able to be set up
A good question. He's asking, can we work on the inflation question? Not that I know of. We concentrate on the stuff you can see now, which is individual galaxies, stars, planets, and the like. And how they got that way is a hard and different question. Most of the evidence that we're going to get on that comes from the arrangement of cosmic structure, how the galaxies are organized into groups in that beautiful cloud that I showed you. But you can already see from the cloud that the traces of the initial spots are lost immediately. So you can set it up a little differently, and you'll just be stuck with complexity. So that means going back to the cosmic microwave background radiation as the main clue that we have left. So we haven't measured everything about it. We're working on that. More satellites are being prepared, more ground-based experiments are being done, and in 10 and 20 or 30 years we'll know a whole lot more about that.
Could you
how issues are settled between the thrust to find life or possible intelligent life and finding out basic cosmological questions.
So he's asking, how do we settle the issues of different scientific thrusts? Well, there's different versions of that. One is, what missions are you going to do? That's a very hard question. We get advice from the National Academy of Sciences. Within this telescope project, or within all of the big observatories, we have competitive proposal writing. So we're expecting well over 1,000 proposals to come in March. And so we'll have a lot of committees to read a lot of reports.
The members of the committee have
Yeah. So we have to choose hundreds of people to be on the committees just to read the thousands of reports. So there's a very organized process, which we already do for the Hubble, and so we'll do something similar. So Hubble is an enormously popular thing, and this will be too. I expect every astronomer in the world is going to have an idea, and we're going to have to read a lot of proposals. But it'll be fun. Some of them will be brilliant, and some of them will be surprising. And we'll say, why didn't the rest of us think of that?
Accept proposals from all over the world?
Yes. So he asked, do we accept proposals from all over the world? And the answer is yes. If you're from an American institution, we'll send you money if we choose you. If you're from another one, we won't. But everyone will get data. After a year, all the data become public. So everyone can play.
Are there command and control issues with going to the L2, which is farther?
His question is, are there command and control issues for use at L2? Basically, it's pretty much similar to anywhere else. Our radio links are good enough. You have to have a bigger dish to send the information that far, but it's very similar. We do have one simplification relative to operating a Hubble. With a Hubble, you're going around the Earth every 90 minutes or so, so whatever observing program you have is probably going to be interrupted by the Earth getting in the way. We don't have that problem in the deep space orbits. So that's a great simplification. So we've decided to do one thing differently, which is we're going to have a queue of observations. When you telescope, do this, then do that, then do that. And when you're finished with this one, go on to the next one. The Hubble observations are all done by calendar. At this particular minute, do this. So we hope that's simpler. So her question is, what are the chances the umbrella gets hit by a rock? Very high. There will be holes in that big thing. There will be holes in the mirrors. About 0.1% of the mirror will be holes by the end of the mission. And we don't care, as far as we know, about either of them. We did have to do one thing, which is surprising to some people. We have to protect the cables that are on the outside. We don't want holes in the cables, because then things are really bad if you miss a wire. Okay, well, thank you.